Today we're going to be talking about integration by trigonometric substitution. And I know that this is a very difficult topic among most calculus students, so I find it best to just jump into an example right off the bat. So if we have the antiderivative of the square root of 1 plus x squared over x dx, how do we evaluate this antiderivative? And so the best way to notice that you want to use trig sub is you want to notice a square root inside of your integrand, and you also want to notice a squared term inside. And so here we'll have x squared as our squared term. And you always want to start off with drawing a triangle. Right angle. And you'll know that with the Pythagorean theorem, use the terms inside of your integrand to create a hypotenuse that looks something like the square root. And so what I mean by that is I have 1's and x's inside of my integrand. So I'll use them to create the square root of 1 plus x squared as my hypotenuse. So I'll have the square root as my hypotenuse of the triangle. And then I'll have x and 1 here, because x squared plus 1, and then we square root the whole thing, that will be equal to the hypotenuse through the Pythagorean theorem. Now you always want to put your theta opposite of the angle to the variable you're doing with respect to. So we're doing it with respect to x, so I'll put theta opposite to x. Now, the next thing you want to do is you want to look at all trigonometric ratios of this right angle triangle. And so usually you start off with sine. So with these 4 trigonometric ratios, you look at all of them and think to yourself, which one is the easiest, most simple looking one? And so for us, it'll be tangent theta is equal to x. And so knowing this, we differentiate both sides with respect to your variable that you're integrating with respect to. So for us, it'll be ddx, but you can do ddt or whatever you need. And I'll have tangent theta on the inside. And that'll be equal to the derivative with respect to x of x. Okay. So in calculus 1, you know how to use the chain rule. So we'll just do, and then the derivative of tangent will be secant squared. So we'll have secant squared theta. And then you use the chain rule and you have d theta dx. On the right hand side, we have the derivative of x. And so that'll just be 1. Okay. So this is what we want. We want this thing, we want an expression that's equal to 1, so we can plug it back into our integral. Next, you want to rewrite your integrand using our trigonometric functions, or ratios. So, in this example, I can see that I have the square root of 1 plus x squared. And that looks very similar to the sine theta, except it's flipped. And if I flip sine theta, I actually get cosecant, because that's the reciprocal identity. So if I have the integral of 1 over sine theta dx, that's equal to the square root of 1 plus x squared over x dx. Now, you can't really do the left side integral because we're doing it in terms of dx, and sine is using theta instead of x, so you have to account for that using the little formula that we made in the yellow box. And so since this is equal to 1, I can just plug it in anywhere, because multiplying by 1 is the same thing as itself. So I'll have 1 over sine theta, and then I'll have secant squared theta times d theta dx multiplied by dx. And this is the one that we want to solve now, okay? So, if you've watched my last video, you'll know that using the rule of substitution, we can say that that this is equal to 1 over sine theta multiplied by secant squared theta times d theta. Okay, and usually when I say by the rule of substitution, okay, 1 over sine theta is the same thing as cosecant, so I'm going to rewrite it as cosecant. d theta. And usually in these integrals, this looks pretty tough, and it doesn't look like something we can easily integrate. You might be able to do integration by parts, but I'm in no mood to do that. So what I'll do is I will represent secant squared as a Pythagorean identity of 1 plus tangent squared theta d theta. Now I'm going to distribute. I'm going to have cosecant theta plus, and then I'll have cosecant theta multiplied by tangent squared theta d theta. Alright. So this can be split into two integrals, right? Because they're both added. So I'll have cosecant theta d theta, and then I'll add another integral of, and I'm going to write it in terms of sine and cosine, because it'll be easier with tangents. So tangent squared sine squared theta over cosine squared theta. And you'll see that one of the signs cancel out, d theta. So the left-hand side is a little bit more difficult to integrate, so I'll start with the right-hand side. So left-hand side, or no, not left side. Left will be saved for later, but for the right side, we'll do it right now. So we have the integral of sine over cosine squared theta d theta, and you can represent this as tangent theta multiplied by 1 over cosine theta, and you can also write that as the integral of tangent theta multiplied by secant theta d theta. Okay, and this is a known integral. If you've studied any basic trig integrals, you'll know that this is going to be equal to secant theta. And I'm gonna hold off on adding the plus c because I'll add it at the end. But this is our final answer for the right side. Now we want to do the left side. And with the left side, the integral of cosecant is a little bit more challenging. Some people memorize this. I wouldn't recommend memorizing it. It's a very basic U substitution, so I'll walk you through it. So we have cosecant theta d theta. And whenever you have something dealing with trigonometry, you usually want to find a clever way to multiply by 1, or find a clever way to add 0 or subtract 0. And so I'm going to do the multiply by 1 trick. So I'm going to say cosecant theta over 1 multiplied by negative cosecant theta plus cotangent theta divided by the same thing. So I'm just multiplying by 1 d theta. Okay, so now since this is multiplied, I can distribute. I will have cosecant, I will have negative cosecant squared theta plus cosecant theta cotangent theta divided by our same denominator. Okay, now you'll recognize that if you can use a U substitution right here. I'll say let U equal negative cosecant theta plus cotangent theta. So I'm letting U equal to the denominator. And you might be asking, why do you do that? Well, because when you do a substitution, you always find the derivative of your substitution. So du d theta, and what is that? So the derivative of cosecant will be negative cosecant cotangent. So that's going to be positive cosecant cotangent. Plus, and then the derivative of cotangent is negative cosecant squared. So I'll have negative cosecant squared theta. And you can recognize that this derivative is equal to the numerator. So using this U substitution, we can find a really clever way to rewrite it as 1 over U multiplied by du d theta with respect to d theta. Okay, and then we say by the rule of substitution that this is equal to 1 over U du. And this is very easy. This is going to be equal to ln of the absolute value of U. Okay, so now we need to figure out what u is. So u, remember, we let u equal to that. So we're just going to plug it back in. So it's equal to ln of the absolute value of negative cosecant theta plus cotangent theta, close the absolute value. I'm going to hold off on the plus c again, because when I add it up together, I have the right-hand side and I have the left-hand side now. So I have secant theta plus this ln. So my final answer will be ln of negative cosecant theta plus cotangent theta. And then I add secant secant squared, right? Oh, secant theta. Just and then I add a plus c at the end, because this is an antiderivative. Okay, so this is the answer of question 1. But because our answer is in terms of theta, so I'll write the answer. This answer is in terms of theta, but our original integrand was in terms of x. And so therefore we must convert back to x in order to accurately display the answer. So our right angle triangle looked like this. This was theta. This was square root of x squared plus 1. This was 1 and this is x. Okay, so cosecant theta is equal to 1 over sine. And so sine theta is opposite over hypotenuse, which is going to be x over the hypotenuse. So then cosecant theta will be equal to the square root divided by x. Cotangent will be 1 over x. And secant will be the 1 over cosine. Right? So secant theta is going to be equal to 1 over cosine. And then cosine is going to be 1 over the hypotenuse. And so then secant theta is equal to x, the square root of x squared plus 1. So we need to use this one, and this one. And then so the way to accurately display the answer is with an ln. We use the absolute value, and then we do the negative cosecant. So we have negative x squared plus 1 divided by x, and then the square root on the top, plus the cotangent. So we have plus 1 over x. Stop the absolute value. Then you add your secant, which is your square root. And you cannot forget to add the plus c at the end. And that's the answer. Okay, moving on to problem 2. We will have another antiderivative. This time it's a little bit more difficult. And we'll have a polynomial inside of our square root on the denominator. So, when you have a polynomial like this, you have to recognize that whenever we do trigonometric substitution, we always look for something like a constant squared minus x squared, or maybe a constant squared plus x squared, or x squared minus a constant squared. Okay, that's what we're looking for in a trigonometric substitution, and I'm not seeing that right here. So we have to find a way to transform this polynomial on the denominator into something like what I just mentioned. And so the trick here is you want to complete the square. So usually you should be very comfortable with completing the square by now, but I will walk you through it. You have x squared plus 2x plus 5, and then we'll move the plus 5 to the other side, so negative 5. And then we're going to take half of the 2, right? So half of 2 is 1, and then 1 squared is 1. So I have 2x plus 1. And then whatever I do to the left side, you have to do to the right side, so plus 1. The left side will be equal to x plus 1 squared, quantity squared. And then I'll move the 4 back around. So that's a negative 4 on the right, so that'll be a plus 4 on the left. Okay. You don't need to include the 0. Okay, so now we can rewrite the entire antiderivative as this completing the square um, version. And I'm going to do one more trick before we start solving this integral. And I don't like the x plus 1 because it looks more complicated with like that. So I'll use a substitution. I'll let w equal to x plus 1. And then dw dx is 1, right? So I'll have this square root, and then w squared plus 4, and then dw dx dx. And then by the rule of substitution, this is going to be equal to the same thing, but you have to explicitly state du. Or no, not du. dw. Okay, now we can actually start doing the trigonometric substitution. So obviously first draw your triangle. It's a very important step. So you have your right angle right there. And we have our hypotenuse. So that's going to be that. And we have w, and we have 2. Right? Because of the Pythagorean theorem, we're going to put theta opposite to w. And we're going to say, okay, look for sine theta. So sine theta is going to be w over my hypotenuse. Cosine theta is going to be very similar to that. Tangent theta is going to be equal to 1 w over 2. And then secant theta is going to be equal to 1 over cosine. So again, look for the simplest one. Which one's the simplest? And usually you'll find that tangent is the most simple. So I guess we're going to be picking that one a lot. Okay, next. Differentiate both sides. So I'm going to differentiate with respect to w, dw of tangent theta is equal to ddw of w over 2. Okay, and then again, using the chain rule, we're going to have secant squared theta multiplied by d theta dw is equal to 1/2. Right? Yeah, 1/2. And then if I multiply both sides by 2, I'll have 2 secant squared theta d theta dw is equal to 1. Okay, this is what we want to use because it's equal to 1. So now, what we want to do is we want to look for something in our integrand that can be represented by one of our trig ratios. And so we can notice that cosine theta looks very similar to our integrand, but there's a 2 on top instead of a 1. And so what we can say is, if we multiply cosine theta by half, 1/2 cosine theta, that's going to be equal to the one with the 1 on top. And that's what we're going to use. So I'm going to have the integral of 1/2 cosine theta, and we have to make sure that we put it in terms of d theta, not dw. So we're going to use this piece, plug it in there. So we're going to have 2 secant squared theta d theta dw. And there's dw on the right side. So now you can notice that the 2 and the 1/2 actually cancel out. And then, oh yeah, and we have to say by the rule of substitution. Right, so we have cosine theta multiplied by secant squared theta. And we're going to have, not in terms of dw, but in terms of d theta. Okay? Now, what we have is we can, what can we do? So, secant can be rewritten, actually, as 1 over cosine squared theta, d theta. And so you can notice that one of the cosines cancel out. You're just going to have the integral of 1 over cosine theta, d theta, which is also equal to the integral of secant theta, d theta. Okay? So now, how do we integrate secant theta? So again, just like the previous example, we have to find a very clever way to multiply by 1. And this might be one of the things that you should memorize, maybe not the prior one. the integral of secant is pretty, it shows up quite a bit. So I'm just gonna walk it with you. So I'm gonna have secant theta over 1 multiplied by secant theta plus tangent theta. And then I divide by the same thing, so I can have it equivalent to 1 d theta. Again, I'll use the distributive property of multiplication, and I'm going to get secant squared theta on the top plus secant theta tangent theta. And then we divide by the same denominator, d theta. What we can have here is we let another u equal to the denominator, just like the previous example. And then obviously we're going to find du d theta. So the derivative of secant, what is the derivative of secant? It is tangent squared theta. Derivative of tangent theta is secant theta tangent theta. Alright, and that looks exactly like the numerator. So we're going to rewrite this thing as 1 over u times du d theta times d theta. And then by the rule of substitution, I know I've written it so many times, we're going to have the integral of 1 over u times du. That's going to be equal to ln of absolute value of u. And u is equal to this thing. So we're going to have, our final answer is going to be ln of secant theta plus tangent theta plus c. Okay? But you cannot leave your final answer like this. This is not complete, because our original problem was in terms of x. Now we have an answer in theta. So what you have to do is you have to convert back to x. So you have to retrace your steps. So what was secant theta? Because we use it in our thing, in our answer. So secant theta was, let's see, secant theta was the square root over 2. So that big square root over 2. And tangent theta, what is tangent theta? Tangent theta is w over 2. So plus w over 2 plus c. Okay, now it looks like we're done. No, we're not. We're in terms of w now. We have to go back in terms of x. So we have to do ln of, and what was w? So we have to look back. What was w? So w was x plus 1. So we have this big square root of x plus 1 squared plus 4 plus w all over 2. Oh no, not plus w. Plus x plus 1 all divided by 2. And the absolute value, and then we do the plus c. Okay, and I think that's the answer. Yep, that should be right. So, thank you for watching, and I'll see you in the next video.